This is a situation or a scenario that maybe one or two of you or all of you have encountered along the way in your machining journey. Encountering a 5-axis suited part when you have a 3-axis mill. What's up guys, Jonathan Dillahay here with 2SM Performance, and I'm back for another episode of the Cam Files for Practical Machinists. So today I have a really cool episode for you guys. This is a situation or a scenario that maybe one or two of you or all of you have encountered along the way in your machining journey. And that would be encountering a 5-axis suited part when you have a 3-axis mill. Now there are several different things you can do in this situation. You can either no quote, or you can go for it, or yeah. So I'm going to show you how I attack this problem. I take on a part with multiple holes on multiple sides with a 3-axis machine in multiple setups, and how to do it the most precise way and the most efficiently. And that's why I love this trade, because there's so many different ways to attack parts, and I love sitting down in front of my desk in my CAM system and just looking at the part in the 3D model and just clearing my mind and going through all the different ways that I would hold the part and set my work coordinate systems and attack the features. So come on, let's do this. So to start things off, I just wanted to discuss a few different reasons and scenarios onto why you would do this on a 3-axis mill. Well, reason number one, taking on a part with multiple features and holes on all different faces and sides of the part would be if your quantity of your PO was less than 10 parts and you did not want to spend the money on outsourcing to a 5-axis shop and waiting on them to finish it. So also, reason number two, say you have a product that you're coming out with for your product line, you want to test fit it inside of an assembly, or you want to test the performance of it, then you would also do that too. This would be like if you didn't have a 3D printer to test it with, or you needed to make it out of metal for the first time to test the true performance of it. This would be ideal. Anything other than these reasons, I would say doing it on a 5-axis machine is optimal. So as you're going to see in this video, it's going to take me 4 or 5 different setups and operations to get this part to where we want it, where it's finished. Where if you have a 5-axis trunnion style machine, you're getting it done in 2 ops, maybe 3. Depends on if you tab your parts or not. I'm not a 5-axis guy. I'm not an expert at that. But there definitely is a place and an advantage for 5-axis machines. Now, what I'm about to do is great if you don't have angled holes on the parts. If you have holes and features on multiple sides of the part, but they're all right-angled perpendicular holes, that's fine. When you get into the compound angled holes, that's when it gets really tricky and you got to go with special fixturing. That is definitely when you want to go with a 5-axis style machine. So the part I'm going to be machining today is called a throttle lever perch. It clamps onto the handlebars of a gas-powered scooter or motorcycle, and it allows the throttle cable to be pulled in from a lever action with a pivot hole, and the perch also clamps onto the handlebar. So that's another reason why there's holes in different locations. And also there's a threaded hole for the kill switch to kill the motor, is also threads into. That's what the tab is for. So these parts were already in existence. These were already designed and made by a previous machinist and engineering group before I acquired the company. So I had to reverse engineer these by hand with a set of calipers. But now that I have a good solid 3D model, it's time to go ahead and make them on my own. On a 5-axis suited part such as this one, when programming to be machined on a 3-axis machine, Tolerances can stack up and error can be introduced to the part every time it's flipped for a subsequent operation. Because raw stock is very rarely ever perfectly square or accurately modeled inside the cam system, I always try to model my stock as accurately as possible. Also, I always try to set my work coordinate systems into the center of the part for each operation. I keep setting my work coordinate systems into the center of the stock until I make a nice part feature that I can pick up off of for even more accuracy in future part operations. As you'll notice in this episode, my strategy is to drill and tap all of my different hole features and get as many part flips out of the way as possible before I start milling away the majority of material. I believe this method increases accuracy by keeping the hole positions perpendicular to each other and having a rigid amount of material to hold on to. When setting my work coordinate systems in the center of the stock, I always probe all the way across on both sides of the stock and then I divide by 2 after finding their true distance. I believe this works better than just edge finding one side and using a set of calipers. I also believe that when doing parts with a lot of flips like this one, the more square your stock is, the better, since it can be more accurately held in place inside the vice jaws or the fixture. Accurately modeling your stock size is really important as well, especially when checking the Continue Rest Machining box in the Fusion 360 stock tab. Since this part is just a prototype, I really took the time to square up the piece of material and get it exactly to size that I wanted. So for Op.1, I had to drill and tap mounting hole for the throttle lever with an extra long 8-32 cut tap and an M6 cut tap for the bolt that actually clamps the lever perch onto the handlebars. I started things off with my trusty old Tool 1 1/4" spot drill. After that finished, I attempted to make a nice hole with my number 28 Cobalt jobber drill for my 8-32 tap. After hearing the drill crunch and snap, I looked at my machine and realized that my feed override was turned up to 150% from squaring up the material. Also, I realized that my drilling cycle was the wrong cycle. I meant to do a deep full retract cycle, but I had a partial retract selected. So I decided to change that back. Squaring up a whole nother new piece of material and starting over again was really fun. The next item on the agenda was to open up the hole to 3/16 to allow for clearance for our threads on the bolt and to also run the tap to make the threads for the lever mount. Once again, you can see me here making sure that my cycle type for the drill is set to deep drilling full retract. We got a little bit of a bird's nest up there. The chips didn't break very well, but at least we don't have a piece of a broken drill in our part. So for the next item on our Op.1 list was the tap drill for the M6 thread that clamps the perch onto the handlebars. Same thing as the last 2 drills, deep drilling cycle, full retract, yada yada yada. You get it. Once more, another clearance hole for the M6 tap and bolt to clamp the perch onto the handlebar, and we're deep drilling again. So once all the tap drill holes and the clearance holes were drilled, it was time to machine the counter bores with a boring cycle using a 1/4" end mill. On both of these counter bores, I have the ramp angle set at 2 degrees, so it's not too aggressive, and we still get a nice finish once it's bored out. Once the counterbores were finished, it was time for the taps themselves. For the 8-32 thread that I'm using to hold on the throttle lever, I am using a carbide cut tap. I don't think these moments right here will ever not scare me, but this time around I found some success, so I'm just happy about that. Next was the M6 tap with the same song and dance. Anytime that a tap runs super deep into a piece of stock like this, I get nervous. And for good reason. But luckily I came out of this one unscathed, so I'm pretty happy about that. For Op.2, I decided to flip my stock 90 degrees on X to drill and tap the 8mm thread kill switch mount hole. Clicking on the colored lines here, you can see how I set my WCS axis orientation and how I set my work offset to center by choosing the stock point and clicking continue rest machining. Here's to give you a little visual of what we're drilling and tapping on Op.2. Once we got our spot drill done doing its thing, it was time for another deep drilling cycle, for which I like to use a G83 with a 50,000 spec. I feel that this kind of gives a good safe zone to where I'm keeping the hole accurate and keeping the drill from walking, and it's also evacuating chips really nicely. If you'll see here, I used the boring cycle with the 1/4" end mill again to actually make a bigger hole than the tap to allow for clearance. You'll see here that I set my stock to leave to negative 50 thousandths, and that was plenty big enough for clearance. Here I'm simulating my rigid tapping cycle after accurately modeling it, just making sure that nothing is going to bind up or break, and then I'm getting all the way through to make a full thread. So for Op.3, I reoriented the part in a way that allowed me to mill out the main features of the part, including the outline and the 7/8 hole for mounting onto the handlebars. As you can see, I'm still setting my WCS in the center of the part since I still have a square piece of stock to work with. Now that I have Op.3 set up and all of my tools touched off, I'm just running a little simulation of my roughing passes with my 1/2" end mill. As you can see, I'm facing the top, and then I am machining the 7/8 hole and then the outline of the part. With everything roughed out, it was time to machine a feature that I like to call the cable nipple. It's designed to accept and hold the end of the throttle cable housing and the throttle cable itself via a slit cut into the front of the perch. As you can see here, I am boring a hole with a 2-degree ramp angle with a 1/8 inch end mill. And with that same end mill, I'm also creating the slit for the throttle cable by selecting this edge geometry and using multiple depths in my passes tab with a step down of 20 thousandths. In my heights tab, I set my top height to model top, and I set my bottom height to the selected contour minus 25 thousandths to make sure there's no burrs when I mill out the pocket on the other side. With that out of the way, it was time to do the finishing pass on the outline of the perch. For my contour selection method, I opted for silhouette. And when I chose silhouette, I chose outer loops only. I'm opting to do this with a 1/2 inch finishing end mill with smoothing selected at 4/10, and I'm going to go at a little bit lower RPM and feed. I also made the finishing pass on the 7/8 hole for the handlebar mount, but I'm also going to make a separate pass with wear comp that can be adjusted later on. For facing the top deck, I opted to use a pocket milling pass, and I had the base of the nipple selected. I also chose to use a bolt nose end mill, 1/2 inch with a 60 thousandths corner radius. So not only could I face the top of this thing, but I could also create the quarter radius around the nipple at the same time. To create the 60 thousandths corner radius at the bottom of the nipple, I opted to select the geometry at the top of the radius on the nipple itself as my line geometry, and then make step overs and come in multiple passes to create a perfect 60 thousandths radius. I chose roughing passes and selected a step over of 25 thousandths. In my heights tab, I selected the bottom of the radius as my bottom height for the tool as the top deck of the perch. Not only did I select the top of my radius as my line geometry for my chain, but I also extended the beginning and end of my tool path to make sure there are no burrs or extra material left over for where the slot would be. I increased the beginning and end of the path by 1/16 of an inch. For the 100 thousandths corner radius on the back corner of the perch clamp, I opted to go with a 3D contour pass with the same 1/2 inch bullnose end mill. I selected my machining boundary by clicking on the face contours that I wanted to machine and setting my tool containment to tool outside boundary. To To make sure the corner was left aesthetically pleasing, I selected machine shallow areas to make sure my step over and my step down were pretty close to make a nice curve. I also selected the box to machine from bottom up. Here, you can see how I selected tool outside boundary as my tool containment setting. To finish off this op, I chose to chamfer all the edges with a 1/4 inch chamfer. Once I finished chamfering the edges, I then deburred the slot with the 1/4 inch chamfer. Unfortunately, I don't think the chamfered edge blended very well with the corner radius 3D contoured chamfer, but maybe I'll use a ball and mill next time and it'll blend better on the other side. This is the second finish pass that I programmed for the 7/8 hole, and as you can see here, I set my compensation type to wear so that I could be able to open up the hole and control the diameter of it from my machine's controller. So I reran this pass a few times, adjusting the wear compensation for my tool number 5 each time until I got the hole to the exact size that I wanted on the inner diameter. With Op 3 done and dusted, we only have 2 more operations before this part is finished. So in this Cam Files episode, hopefully I explained to you why doing all your holes and getting all your flips out of the way on a 5-axis suited style part in a 3-axis machine is important. I hope you guys got something good out of this episode, and I'm really looking forward to putting out the next one where I'll finish this part with the next operations. If you have any comments or suggestions, please drop them in the comments. Until next time, it's been real. It's Jonathan Dillahay from 2S Performance, bringing you the Cam Files from Practical Machinist. Peace.